Hi everybody, as promised, I'm already back. We will talk today about the control board of Talos, which is the heart of the system. It's where your creativity as a designer comes to play a really big role because there are so many degrees of freedom, but it's also where you are almost certainly going to make mistakes, at least I am, because it's complex. It involves a lot of timing and it's difficult to run a simulation in your head about everything you're doing. So you're more dependent on simulations here. Before I talk about the control board, let me just let you know that in episode 12, which I uploaded yesterday at the time I'm recording this, I already found 2 mistakes I made in the instruction set architecture. They are corrected in the spreadsheet that is on the repository already. I will talk about those mistakes and explain to you why they are mistakes at the end of this video, because what we will cover today will be very useful to help explain why they were mistakes. So let's dive right into the control board. The first thing that we need to understand is how timing will be governed, and that's why I have this little diagram in front of me right now. This is the clock. That's the main clock of Talos. It has rising edges and falling edges. Usually the chips respond to the rising edge. That's when states change. In normal 74 series TTL logic, states change on the rising edge. That's when stuff happens. But for Talos, in the control part, we will need the concept of a two-phase clock. And this is what I want to explain with this diagram. What we want to do is the following. We want to set the control lines that we reviewed in the previous episode, all the output enables, load enables, count enables, read and write strobes, and so on and so forth. We want to set them in advance of a rising edge of the clock, because in the rising edge, that's when stuff happens. So if you want to prepare for what's going to happen, you have to prepare in advance. So we want the control lines to be set on the falling edge of the clock. So all the load enables and output enables are set on the falling edge. So for instance, if you do A equals B, then you set output enable for B and load enable for A on this falling edge. You wait for everything to stabilize for half a clock cycle, and then on the rising edge of the clock, you actually latch the value that is being transferred from B to A, or you latch the result register of the ALU. The rising edge of the clock is when you latch the data that has been communicated or computed. But to decide what computation you want to do or what communication you want to do, we will use the falling edge of the clock to set the control lines. And on the rising edge, with the control lines already set for half a cycle and everything stabilized, now we will actually latch. We will latch it in the registers in which load enable was activated, or we will latch it in memory with the write strobe, which is active low. That's why this N of negative here. So that's the idea of a two-phase clock. In practice, we will have the main clock and we will have another clock, which is the inverse of the main clock. We will have a clock that will have a rising edge as the main clock has a falling edge like this. And I will call it N clock for the negative clock, which is just the inverted main clock. And the chips will respond to this rising edge, but this rising edge will correspond to a falling edge of the main clock. So we call it a two-phase clock because this clock is the main clock, so that has a certain phase, and this one has a 180-degree phase shift compared to the main clock. If you are not aware of the concept of degrees to determine phase, you can forget about it. All it matters is that there will be an end clock that is the inverse of the main clock. And whatever happens on the rising edge of the reversed clock will correspond to the falling edge of the main clock. That's basically it. Now, keep in mind that latches may not be instantaneous. If you're latching into a register, like 8 flip-flops, it's almost instantaneous. Because the lines that need to be latched will be stable. They will have had half a clock cycle to stabilize. So when the rising edge of the clock hits, the flip-flop would just almost instantly capture whatever is on those lines. But when it comes to memory and the right strobe, the WR, it takes a little longer, and you have to look at the data sheet of the memory chip one is using to see how long you have to keep the buses stable until the write actually completes. It is not instantaneous. So during this interval that you have to wait, the address bus has to remain stable and the data bus has to remain stable in case you're doing a write. Well, that's a write. And only after this interval, from this point on, now you can change the address bus and the data bus. So we can't change the buses immediately after the rising edge of the main clock, because the latching process takes a little while. It's not instantaneous. So the address and the data that you're trying to write to memory need to remain stable for a little while. Usually that's in the order of 50 nanoseconds, maybe less if you buy a more expensive chip. So that's what I wanted to introduce to you first. We can now look at the draft of the control circuit. I haven't run any simulation yet, which means that there almost certainly are errors in what you're seeing right now. Like in the previous episode, I'm also asking for your help on this one. Despite the usually authoritative tone I take when I explain things, I am not sure that I've done everything right in here, so please be skeptical of everything I'm saying, because I may be fooling myself and fooling you unintentionally. So if you find an error, please let me know in the comment section below. I will be reading all comments just like last time. So just help me parse this whole thing and detect if I'm fooling myself somewhere, despite my authoritative tone, which I have developed over 25 years in the high-tech industry. It becomes a survival need to develop that tone, but I don't really mean to be authoritative, because I'm as prone to error as everybody else. Anyway, so let me give you an overview of the idea first. It all starts here at the top with the opcode immediate byte. This is a byte that comes from instruction memory. Remember, Talos is a Harvard architecture, so data and instruction memories are separate. This is the data bus from the instruction memory. It's whatever the instruction memory is replying to when you drive its address bus. Usually it's an opcode. So let's pretend this is an opcode. It goes in two ways. It goes to the left to an instruction register, which is supposed to hold an opcode, and it can go to the right to an immediate register, which is supposed to hold an immediate byte, not an opcode. But let's pretend that there are no immediates first, only opcodes. So this register here will latch this value on the rising edge of the internal clock of the control card. And the internal clock of the control card, as you can see here, here's the main clock. Let me increase the size so you see it. This card will get the main clock here as input, but then it will invert it. This is an inverter. It will invert it and we will get the end clock, or the negative clock. And that's the clock that is used on this card. You will see MN clock in several places, like here. I will explain what the M stands for. It stands for masked. But you can pretend that this is just the N clock, and the N clock goes everywhere on this board. So on the rising edge of the N clock, or the falling edge of the main clock, this byte will be latched onto the instruction register, which will contain the opcode, and it goes down to a 16-bit bus, which contains that opcode in the register, and then in addition to that, 8 flags that you see there. Let's zoom in and look more carefully at those 8 flags. 6 of them you're familiar with. Those are the flags that come from the ALU. The 0 flag low, 0 flag high, sign flag low, sign flag high, and carry flag low and carry flag high. 2 of them, OMF and IMF, which stand for incoming mail flag and outgoing mail flag, I will discuss in shortly. They are new flags. The point is that you get then a 16-bit value, which is an address. That address is 4 64 kilobyte memories. Those 4 memories that I just scrolled in front of you. Now notice that this is not a very efficient way of doing things. If I were designing a chip, I wouldn't do it this way, because for each value of an opcode, we will get 256 lines in the memory, each line corresponding to a different permutation of the 8 flags. Now, most instructions do not care about the flags at all. Only the jumps care about the flags, the conditional jumps. So 15 instructions care about the flags. The other, 187 don't care about the flags. And yet you're going to waste 255 addresses in these memories per instruction, for each one of those 187 instructions that don't care about the flags. Now, is this optimal? No, it's insane. But when you're doing a design at the board level, it is entirely sane and economically very reasonable. Because these memories, I will be using flash memories. I just ordered a bunch of 256 kilobyte memories from Halt in Germany for €2.5 each. 256 kilobytes parallel flash. And I will be using only 64, and it's only €2.5 per memory. So yeah, it makes sense at a board level to waste a lot of addresses and save decoding logic. If you would decode the opcode using logic instead of memory, you would need lots of chips, lots of TTL chips, or some expensive PLA chips. And instead, I will be using €10 worth of memory in total. And the smallest of these flash memories is 128 kilobytes. You cannot buy less than that. They all fit in the same pinout. So it does make sense to waste a lot of memory, which is what I did. Now, when I do an FPGA implementation, if I ever do it, I'm definitely not going to do this. I will still have memories here, but they will not include the flags in the address. I will use only the opcode in the address. So these memories inside the FPGA, these 4 memories inside the FPGA, will only need to contain 256 bytes each. Because, with a byte as address, you get to the power of 8 addresses, which is 256. And I will use logic to split out the jump instructions. There are only 15 of them. The way I did the encoding, if you remember from the previous episodes, the jumps are all in the high part of the opcode space. They're all close to 255. And for the conditional jumps, all conditional jumps have the 4 most significant bits of the opcode as 1. So it's very easy to identify an opcode as a jump or not. If they are not a jump, then you just address 256 byte memories in the FPGA. If they are a jump, then you use some decoding logic. It's only 15 conditional jumps anyway. So that's how I'm going to do it in the FPGA. But here, I'm not going to make that distinction whether it's a jump or not. Everything goes through the memories because memories on a board, if you buy memory chips, they are so cheap. They are just expensive in an FPGA. Okay, so the opcode is latched there. We add the flags to form an address, and the resulting 16-bit address will address these 4 memories with the exact same address. And the memories will reply with 8 values each, totaling 32, and in the next clock cycle, the output of the memories will be latched in these 4 registers. And from the registers, they go into these 4 transceivers, which will drive out the control values. And the control values are here. Each memory will hold 8 of the control values. We've discussed them all in a previous episode, or almost all of them, and that's where they come out. And from here, they go to the rest of the system, to other boards, except 4 of them. This one, these two, and these 2 here, which have a different shape, they remain within this board. They are control bits that will control logic within the control card itself. The others, which have the form of a little arrow, they will go through the back plane to the other boards and control the rest of the circuits in the CPU. So that's basically it. This is a 3-stage pipeline. On the first stage, the first clock cycle, the instruction register will latch the output of the instruction memory. On the next clock cycle, or the next stage, the output of these decoding memories will be latched by these registers. That's the second stage of the pipeline. And in the third stage, with these control bits already going to the rest of the system, we will actually execute the operations that are determined by the values of these control bits. That's basically it. That's a 3-stage pipeline. And it's a pipeline because the moment IR is fetching the current value coming from the instruction memory, at that same time that IR is latching that value, these registers will be latching the output of these memories for the previous opcode. And at the same time, the rest of the system will be executing 2 opcodes before. So at every cycle, the IR will latch a value. These registers will latch the decoded instruction word from the memories, and the rest of the system will be executing an instruction. Every cycle, all 3 things happen, but they happen for different instructions. So each instruction has a latency of 3 cycles. In the first cycle, IR fetches the opcode. In the second cycle, these pipeline registers latch the decoded instruction word. And in the third cycle, stuff is actually executed. But at the same time, the next instruction and the next 2 instructions will be already in the pipeline, but in different pipeline stages. That's basically what RISC means. That's what pipelined architectures mean. You can have CISC pipelined as well. The EZ80 is a pipelined CISC, but if you look internally, they really are RISC. Okay, so now let's get into the complications. When we do load immediates, where do the immediates come from? Well, they also come from here, from the instruction memory. Immediates are part of the instructions. But an opcode is already an entire byte, so the immediate for a load immediate instruction can only be in the next address in the instruction memory. So we have to discern whether what's coming from the instruction memory is an opcode or an immediate, and then latch the value in the correct register. If it is an opcode, we latch it here. If it is an immediate, we latch it here in the immediate register. So how does this work? This is what is performed, the function that is performed by this circuit, which I will explain in the next page, much easier than seeing chips. But let me tell you first what the circuit does, and then I will explain how it does it. What this circuit does is the following. It keeps on spying this value here that comes from the instruction memory. If it detects that that value is a opcode corresponding to a load immediate, then in the next cycle, it will not clock this register, and it will clock this register instead. So the next value goes from here to this register instead of from here to the IR register. And then in the cycle after that, everything goes back to normal. This register is clocked and this one is not. So this circuit here decides whether IR or IMM1 is clocked based on the value that's coming out of the instruction memory. Now, suppose that you do a load immediate. What will happen first is that we will have an opcode. So the IR will be clocked, and the opcode corresponding to the load immediate will be stored here. But then in the next cycle, because this circuit knows it has just loaded the opcode for the load immediate, in the next cycle, the next value that shows up at the output of the instruction memory will be latched here, because this circuit will clock this register and not the IR register. So at the end of this process, we will have the opcode of the load immediate here, and we will have the actual immediate value there. And then they have to flow down through the pipeline in sync. And that's why there is a second register here that will just latch the same value that was in the first register, but because multiple instructions are going through the pipeline at the same time, we have to replicate the registers across the pipeline so everything remains in sync. What you want to make sure is that when the decoded instruction word is already available on these registers, then the immediate value corresponding to the instruction here will be there. If you take the immediate value from here, that will be the immediate of the next instruction that will not correspond to the instruction word in these 4 pipeline registers. That's the idea. Now, talking about this right now, it occurred to me that I made a mistake. No, this is correct. I was wondering, do I need another immediate register? But I don't. No, I may need an extra immediate register. Otherwise, I get a race condition. It's a 3-stage pipeline. And I have only... I have to think about it more carefully. Well, if you know the answer, put it in the comment section below, please, to help me out. But right now, as I'm talking to you about it, I thought about it before and I decided against adding another pipeline register here. Maybe I was right then. I have to think about it more carefully. I'll think about it after I finish recording this video. The question is whether I need IMM3 to keep everything in sync or not. I have to give it further thought. If I need to, then it's just a matter of adding another pipeline register there. It's no big deal. I don't think I do though. No, I may need to. Well, I'll think about it afterwards. Now, how does this work? How does this circuit knows whether to clock IR or IMM1, depending on whether you have an opcode or an immediate value coming from instruction memory? I'll explain this here in this little mock-up circuit. It's the same circuit that you saw before, that you saw here. The 7474 are 2 flip-flops and the 7408 are 4 AND gates. So the circuit being implemented here are these 2 circuits that you see there. But I will explain this first, which is the logic that determines which register will be clocked. Here we have a PLA. I'm using a PLA because, you see, you will need a EEPROM programmer anyway to program these memories, which will be flash memories. But you can use an EEPROM programmer. Most of them are compatible with flash. So if you have an EEPROM programmer anyway, you might as well program a PLA and save, I don't know, 5-6 chips, maybe more, that I would otherwise need. I can open this up to show you what this is. And this is a typical PLA, so you have the inputs here on the top, 8 inputs, numbered from 0 to 7. These are the bits of the opcode or the immediate. Then each of these bits can go raw or inverted down a matrix. And then you have multi-port AND gates that will end the values that you choose. So, for instance, this first AND gate will end bit 0 with the inverse of bit 1 with bits 2, 3, 4, 5, and 6. In other words, this AND will be a 1 when the input value here is itself a 1. This AND will be a 1 when the input value is a 2 because I'm inverting bit 1. This AND will be 1 when the input value is a 3, and so on and so forth until 6. And then we have a OR. So if any of the input values is 1, 2, 3, 4, or 6, then we'll have a 1 at the end. And what's the opcode of the load immediate instructions that we saw in the previous episode? Well, they range from 1 to 6. Those are the load immediate opcodes. So if what's coming in is a load immediate opcode, the output E will be a 1. Otherwise, it will be a 0. That's basically what this PLA does. And then what happens is the following. Let's ignore this AND gate for the moment. I'll explain this later. This result of the PLA goes into the D input of the flip-flop. This D will be a 1 in case the opcode is a load immediate, and it will be a 0 in all other cases. And then we have the negative clock, which is basically active in the falling edge of the main clock. And that's what will clock the flip-flop. So on this active edge of the clock, which is the falling edge of the main clock, D will go to Q. So if the opcode was a load immediate, Q will become 1 in the next cycle, because we have to wait for this clock. Only then Q becomes 1. And then the 1 will go into an AND. The other input of this AND is the negative clock. So the negative clock will be passed to the immediate register. And the immediate register will clock. In other words, immediately after a load immediate, in the next cycle, the immediate register will be clocked and the instruction register will not, because this is the complementary output. If this Q is 1, then this is 0. And if this is 0, then the clock is not passed to the instruction register. Now, if the opcode is not a load immediate, then this value will be 0, and then the other input of the AND doesn't matter. D will be 0. On the next clock, D will go to Q, Q will be 0, and the immediate register will not get clocked. But this will be a 1, so the instruction register will get the clock correctly, because that's an opcode now and not an immediate value. Now, why this feedback loop here, going back into the end? The reason is the following. Suppose that you do have a load immediate opcode. So this will be 1. And then pretend that you don't have this AND gate here. The 1 goes straight to the D. So the next cycle, the immediate will be clocked. But suppose that the immediate value is itself 1, 2, 3, 4, 5, or 6. Then this PLA will still say, oh, it's a load immediate opcode, and in the cycle after that, the immediate register will get a clock, even though the next instruction will be an opcode and not the immediate. So you see, if the immediate value corresponds to the value of the opcode of an LDI instruction, the circuit would not work. How do we solve that? Well, we do the following. We take this feedback here from the negative output of the flip-flop and we wire that back in. If the previous instruction was an opcode, then we know that this was a 1, because that's what clocks the instruction register for opcodes. So this was a 1, which means that this is a 1. And if the value coming after that is a load immediate, or even a load immediate instruction, then 1 plus 1 will be a 1 and everything will work. But suppose that in the previous cycle, this was a 0, meaning this was a 1. So we have just loaded an immediate into the immediate register. We know that what's coming from instruction memory after that can no longer be an immediate, because all immediates are 8 bits in Talos. So the next content of the instruction memory after an immediate is necessarily an opcode. So even if the immediate value was 1, 2, 3, 4, 5, or 6, it doesn't matter, because if this was a 1, when we just loaded the immediate value, this will be a 0, and this 0 will mask away the output of the PLA. So in the next cycle, we will always go to the instruction register, regardless of the value of the immediate we have just latched. I hope this made sense to you. But this is basically what's happening here on the top part of this circuit. Now, something else is involved, and this something else is the following. One of the inputs to the CPU, which I show here, needs to be a halt operation, because Talos' CPU will communicate with the rest of the system via DMA, direct memory access. So the rest of the system, like the I/O controller, needs to be able to tell the Talos CPU to halt and tri-state the buses, so the I/O controller can use the buses to manipulate memory. That's how it will communicate with Talos. So we need a halt instruction. And the halt instruction will determine whether the CPU will be clocked or not. So if you go back to the top, this is what's happening here on the bottom part until here. This is what's happening here. And the circuit mapped in here is the same as this, so I will explain it here. So the negative clock is here, unmasked, and it goes into the clock input of a flip-flop. The D input is the halt signal. So if it's not active, this will be 1 because it's active low. If it's not active, it's a 1. And then on the next clock cycle, the 1 will go to the output Q into this AND gate, and it will not mask the AND clock, which will then become the masked AND clock. So nothing happens. You just get AND clock here when there is no halt. But when there is a halt, this value here will be 0. In the next negative clock cycle, clock edge, or the rising edge of the negative clock or the falling edge of the main clock, this 0 will be passed to Q, and this input of the AND gate will be a 0, and therefore the system will not get a clock. Because whatever you end with 0 is 0, regardless of what is on the other input. That's how the halt stops everything on its tracks. It does something else. When the system is halted, this is 0, therefore on the rising edge of the negative clock, this will be 0, but this is the negated output, this will be a 1. And what is this? This is output enable. This output enable is what goes here. Is what enables the transceivers that put out the control signals. In a halt state, NOE will be 1, but it's active low. So these transceivers will tri-state. If this tri-state, the values of the control lines will be 0 because the control lines are pulled down by these resistors. These are pull down resistors. So if these lines here are not driving, if they tri-state, then all the control bits, all the control lines will be 0, which will basically tri-state every single transceiver and free up the buses for the I/O controller to use to access all the memories, instruction memory, data memory, everything. That's how the thing works. Notice that the pull downs here are critical. So this is what this little circuit does. Now there is one thing I want to add. You might say, well, why use a flip-flop? We could pass the halt straight to the AND gate. Well, we can't, and the reason is we cannot halt the Talos CPU at an arbitrary moment. Because imagine that the Talos CPU is in the middle of performing a memory write operation. It's writing to memory. And that write operation takes a little while. We've just talked about it. It takes in the order of 50 seconds, 50 nanoseconds, depending on the chip you're using. If we halt and tri-state the buses in the middle of that writing process, you may write some of the bits and others will not be written, or the address lines can float and you write to the wrong address in memory, you get an error. You cannot halt a CPU at an arbitrary moment. There are moments in which it's safe to halt the CPU, and in this case, it is safe to halt the CPU on the rising edge of the negative clock. In other words, on the falling edge of the main clock, because on the falling edge of the main clock, there are no latches. Nothing is being latched. We are just setting up the control lines. If you halt at that point, that's okay. And when you unhalt, you have to unhalt at that exact same point again, which is what this will do. Because this flip-flop is clocked by the negative clock, it will halt or unhalt the CPU only on the falling edge of the main clock, when nothing's happening except preparation. So that's why there is a flip-flop here. Remember, you can never halt a state machine, let alone a CPU, at an arbitrary moment. You have to know when to do that. And the Z80 has all of this built in. The 6502 doesn't. It creates a headache if you're doing DMA. I talked about that at Cerberus. I don't want to get back to that. From a processor designer's perspective, the 6502 is... I mean, it was very cheap, and it has merits for being very cheap and very fast given the price. But no, I don't like to work with that thing. Therefore, I'm not designing like that thing. We have two separate strobes here, read and write, like the Z80, unlike the 6502, which has only one line for both strobes. And the halt is properly managed. You don't have to manage it with logic outside the CPU. All right. So this is this top part here. You understand it now. You understand all of this. Now there is one more point I need to explain. One of these lines here, you see, go into an AND gate before getting into the transceiver. That line is the right strobe. Let me make it bigger so you can see it better. Here is the right strobe. The right strobe, before it gets sent to the rest of the system, it is ended with the main clock. And the reason is the following. Memory takes time to write the value of the data bus into its internal state holding elements. It's not instantaneous. A register does it almost instantaneously, but an SRAM takes a little while. So you have to wait for the address bus and the data bus during a write to memory cycle. You have to wait for those buses to stabilize, for the address value on the address bus to be stable and not floating or oscillating, for the data value in the data bus to be stable and not floating and oscillating. And only after you've given half a clock cycle for them to be stable, then you can hit the right strobe and tell the memory, okay, now latch this value on that address, because the value and the address are now stable. Therefore, we have to end the right strobe with the clock. Otherwise, you will have a right strobe on the falling edge of the main clock, while the address and the data buses are still not stable. The values are still fluctuating because the electrical signals are still, being communicated. And then you may write garbage on a random address, and you can never recover from that. To avoid that, we have to wait for the address bus and the data bus to be stable before we issue the right strobe. Therefore, we have to end it with the main clock, because the control line itself coming out of this register, that control line will be activated on the falling edge of the main clock. So to wait until the rising edge of the main clock, we have to end it with the main clock. That's the idea. And unfortunately, we need an extra end chip, a 7408, just to use one gate. And I really don't like it. I mean, this is so tight, right? We use all 4 gates and all 2 flip-flops here. It's very tight. This part, which I will still explain, is also quite tight. But here, this looks like the work of a stagiaire, somebody fresh out of the university. But it's not my fault this time, and it's just the circuit is such that we can't avoid adding a chip just for 1 gate. Yeah, I hate it, but it is what it is. Which brings us to this part, which is the final element of this whole thing, and almost the end of this video. Let's go to it. Zoom into it. Some of it's trivial. Like these 2 control lines here, they come from here. They are the immediate registers output enable. So immediate high output enable, immediate low output enable. Here they are active high because we want all bits come in the decoded control word to be active high, so the reset makes sense. But since these two transceivers have the output enable as active low, these two bits need to be inverted, and that's exactly what's happening here. They just get inverted before they go to the two transceivers. And when you have a load immediate instruction, these two lines will be active. They will be 1 here and they will be 0 there. So the value of the immediate register in the pipeline will drive the internal bus high and or the internal bus low, and therefore one can latch the immediate into the general purpose registers A high, A low, B high, and B low. That's the idea. So that's the top part. Very simple, trivial even. The first inverter in the bottom part just inverts the clock. So we get this two-phase clock. That's the main clock and that's the negative clock. And they go elsewhere in the circuit. These are the tunnels. Using this notation here avoids the need to draw lines that cut across the entire circuit and make it very difficult to understand. And then we have those two extra control bits that I mentioned last time but didn't explain. I will explain them now. They also come here from the decoded instruction word. And their meaning in English is, for this first case here, it's set outgoing mail flag, and this one here is clear incoming mail flag. Now the mail flag is a system to allow the CPU and the I/O controller or the DMA controller to know if they have already read a message that has been sent to them via the main memory. So say that the I/O controller has written a byte to memory that the CPU should read. The CPU has to tell the I/O controller when it will have already read that byte, so the I/O controller can send the next byte and overwrite the previous one. But until the CPU says, okay, I have read my mail already, the I/O controller cannot overwrite it. The same works the other way around. If the CPU is sending a message to the I/O controller via main memory, it will set the outgoing mail flag, and it will not send another message until the I/O controller has cleared the outgoing mail flag. That's the idea. And this whole thing works with these two chips here, which I'll open up. 4 OR gates and 2 flip-flops. And the circuit that they implement is the same circuit as here, this. So I'll explain it here because it's easier. So let's talk first about the outgoing mail flag. That's the flag that is set by the CPU after it has sent a message to the I/O controller. So the CPU, through this line here, set outgoing mail flag, and this line comes from the instruction word here, set outgoing mail flag. When this is a 1, the inverter will make sure that this is a 0, and that's the set input of the flip-flop, and it's active low. So when this is a 0, the output Q, or OMF, will be a 1. In other words, we will have set the outgoing mail flag, telling the I/O controller there is a message for you in main memory. Now, after the I/O controller has read that message, it can set this input bit, this is an input to the Talos CPU, clear outgoing mail flag. And when this is 0, this is the reset line of the flip-flop. The flip-flop will be reset and Q will be 0, and therefore OMF will be 0, indicating to the CPU, I have read my mail, you can send me another message. You can overwrite the previous one because I have already read it. And of course, the reset line, the global reset line, should also be able to clear the outgoing mail flag. The reset should reset everything. That's why this OR gate. The exact same thing here on the other side, except that the roles are now reversed. Now it is the I/O controller through an input pin to the CPU that can set incoming mail flag after it has put a message in main memory for the CPU. It puts the message in main memory for the CPU, then it activates this line, which will set the Q output of the flip-flop, and the incoming mail flag will be 1, telling the CPU there is mail for you in main memory. After the CPU will have read that message in main memory, it can set through the clear incoming mail flag, which is coming from the instruction word over here. It can assert the reset input of the flip-flop and clear the incoming mail flag, which will go back to 0. And if it's 0, the CPU can read it and know, okay, the message I sent has already been read. I can send another message and override that address in main memory. And just like before, a global reset should also be able to clear or reset the incoming mail flag. And that's it. That's what is implemented here in these 2 flip-flops and 4 OR gates. It's more complicated to see when you see the chip, but of course I'm using chips here and not gates because I'm going to run a simulation of the system, and then I want to simulate the actual system that I will build. And the system that I will build uses chips and not abstract logic gates. But to explain, I converted that to logic gates. So this is it, ladies and gentlemen. Hopefully this works. I have to give it a better thought about, do I need another pipeline register for the immediate value? I'll think about it myself, but why don't you think about it yourself as well as a kind of exercise? This is not an artificial exercise in the sense that I myself had the honest doubt right now, so I'm not sending you to do silly homework, answers that I already have. Give it a thought yourself. It may help you understand what's happening. And then next time, in the next episode, I will be running a simulation of this board, not of the entire system. That's probably too much work. I will probably run that in the hardware itself. But I have to simulate at least everything you've seen here. So I have to add some dip switches here on top and fill these memories with some values to see what's happening, to make sure that this circuit here is correct. And then I'll go and make a PCB for it. And after the control logic PCB is done, we will be one PCB short of the end. We will need the backplane PCB, which will also contain system memory for instructions, for data, will contain the I/O controller and the interfaces to the rest of the world. But that should be all trivial and easy to do. This is the more involved part of the whole system. The mistakes that will be made, that will require me to respin a PCB or two, I am sure those mistakes will be here and not in the backplane board, not in the main board. Mistakes will happen now, probably already happened. Anyway, if you have comments, know how to correct me, know you spotted some error, please let me know in the comment section below, and I will be back next time with a simulation. Thanks for watching. Till next time. Oh wait, not that fast. I had promised you to talk about the mistakes I made in the previous episode, episode 12. I already corrected that mistake, but I reverted it. I put the mistake back on this line here, line 43, to illustrate the problem. The problem happens during store in memory operations. The other operations we can get away with what I did, but for the store in memory operations we can't. This is what I did before. This is an instruction that would take the contents of register A high and store them in the addressing memory indicated by the contents of address register 1 or AR1, and concurrently it will increment the value in AR1. Now this is a problem. This leads to a race condition because remember, latches are done on the rising edge of the main clock. On the falling edge of the main clock, before that, half a cycle earlier, we will set these control lines here to the respective registers. All these control lines here entailed by this store instruction, all the way until here. And that will mean that the output enable of AR1 will be activated. So for instance, here, AR1 output enable is 1 on the falling edge of the main clock. So AR1 can drive the contents of the external address bus. Remember, this is AR1, here is AR1, and through these two transceivers here, and this line here, it drives the external address bus, telling memory where we want to store the value in the data bus. However, the right strobe, which we've just talked about, the right strobe will only come in the rising edge of the main clock. And then after that, you have to wait for at least about 50 nanoseconds before you change the address or the data bus. The problem is that if you are doing an increment of the address register at the same time that you're driving the external address bus with it, you will get a race condition. The value in AR1 will begin changing before the right strobe will have completed and the memory will have latched the value on the data bus. And because that AR1 value will be changing, you will be already telling the memory that it should write into a different address, because the address is changing on the address bus before the completion of those 50 nanoseconds. And you could write the value in the wrong address because of that. That's a race condition. So we have to avoid that. And the way to avoid that is to always make sure that whenever you are incrementing an address register, you are not using that address register to drive a bus at the same time. You increment the other address register. So instead of incrementing AR1, we just add a parallel operation, AR2 ++. And now it is correct. Now I'm driving the external address bus with the contents of AR1, which are not changing, and in parallel, I am incrementing the contents of AR2, which are not driving any bus. So that's the change that was made everywhere. Whenever a bus is being driven by one address register, it's the other address register that is incremented, and I do it consequentially here. All instructions are like this. I never use the same address register as both a source and a destination of operations in the same cycle. That's what I should have done from the beginning. The other error I had made was for the jump instructions here. There are 17 of them, but this is an unconditional jump, so 16 conditional jumps. But in any case, for all jumps, the bit that changes is, of course, the PCLE, or the program counter load enable. You want to enable the program counter to latch the address in the jump address register. That's what a jump means. But I had forgotten to activate the program counter output enable, because under all circumstances, we have to drive the address line of the instruction memory with the program counter. So this is a redundant line. I could have replaced it by just pulling up that line, because it's always on anyway. But that would give me 31 control lines. And per force, I have to use 4 memories anyway, whether it's 30, 29, or 32, I need 4 memories. So I would have a bit missing in the memory, so I decided to keep the one there in case somebody uses the available space. There is available space here. There is a gap in the numbering. So between 186 and 239, there are opcodes still available. And maybe someone thinks about an instruction that doesn't want to update the program counter. I think it would be tricky. I'm not sure it would be a clean thing to do. I am not going to do it myself. But Talos will be done in such a way that it will be possible to do it, because the program counter output enable is just a control line that can be decoded from the memories just like any other control line. All right, now this is really it. Thanks for watching. I'll see you next time.